So next we have exercise 16. In this we have our usual matrix algebra Fn of all n by n matrices over the field F, and in it S denotes the set of all symmetric elements. That means the elements in S are the symmetric matrices. We have to prove that the subring of Fn generated by this S is equal to Fn, is all of Fn. Let us recall that as an algebra, Fn is also a ring. So of course we can think of its subrings, and the subring that S will generate is by definition the smallest subring of Fn containing S, and we have to prove that that is equal to Fn. So let's see the solution. We start the solution by naming the subring something, say K. Let K be the subring of Fn generated by S. Now the first observation about this K is this. For any index I, let us consider the matrix EII. Do you recall what this EII is? EII is the matrix, n by n matrix, whose ith row, ith column entry is equal to 1 and all the other entries are 0. And it's a diagonal matrix because this is a diagonal position, ith diagonal position on the leading diagonal. So it's a symmetric matrix automatically, and that is why any such EII belongs to S. And in fact, if you multiply any such EII by a scalar, any scalar alpha coming from the field, then this alpha times EII will also be a symmetric matrix. It will be that matrix whose ith diagonal element is alpha and all the other elements are 0. So this is also a diagonal matrix and as a result a symmetric matrix. And that is why any such product alpha times EII belongs to the subring K generated by S. Why? Because K contains S as a subset, that's why. So we get this fact almost immediately, that for any such index I and any scalar alpha coming from the field, alpha times EII belongs to K. Alright, next we do this. We take two indices I and j, again between 1 and n, including, there can be 1, they can be n, all possibilities are there, but this time I and j are different indices, unlike this one where both of them were the same index. Now we already know that EII belongs to S, but what about this second matrix, which is the sum of EIJ and EJI? EIJ is the matrix whose ith row, jth column entry is 1 and all the other entries are 0. And EJI is the matrix whose jth row, ith column entry is 1 and all the other entries are 0. So if you add them up, obviously you are going to get a symmetric matrix where the leading diagonal is like this, and say the ijth position is here where you have a 1 and the jith position is here where also you have 1, elsewhere it's 0. Now if you multiply these two symmetric matrices, then see, being elements in S, after all they are also elements in the subring K, and the subring K itself is closed under multiplication because it's a subring, and that is why their product will belong to K. But what is their product? By the distributive law that we have in our matrix algebra, the product first of all will be this EII times EIJ, and then plus EII times EJI. Now recall the rule for multiplying two such E's. If the inner indices means this one, this I and this I, if they are equal, then the product is again another such E where you write the outer indices. In other words, because here you have I and I, you will write in place of this product EIJ. So that way you are having EIJ. But what about that other product EII times EJI? They are the inner indices are I and j which are not equal, and in this case the product will be 0. That is why we do not have anything else here. And we end up proving that just like any EII ultimately is in K, the EIJs are also in K. Actually here for EIIs we were immediately able to conclude a little more, namely that if you multiply any EII by alpha, then because you are still getting a symmetric matrix, so all such products belong to K. Unfortunately, here you cannot do that. Why? Because what is this matrix? In this matrix, the non-zero entry 1 appears at the ijth location, which is an off diagonal location. So if you multiply that by some scalar, and in fact this matrix itself is not a symmetric matrix, note that fact. Okay, although the product which is equal to this belongs to K, but this matrix itself is not in S, it belongs to the subring K. And multiplying this by any alpha also won't give you a symmetric matrix. So that way you cannot conclude like this one, that alpha times Eij belongs to K. But we need that, and we are going to achieve that in a different manner. Let's see how. So let us next do this. We choose any scalar alpha in F, and for that scalar we consider this matrix A in Fn, whose ith row jth column entry is alpha ij, and alpha ij is equal to alpha for all I and j. So that means this matrix A is the n by n matrix, all of whose entries are equal to that scalar alpha, 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 alpha everywhere. Alright. Then obviously it's a symmetric matrix. Everywhere you have the same element, automatically it's symmetric, because if you take its transpose, it is again that same matrix. If you transform the rows into columns and columns into rows, nothing changes. And as such, this A belongs to S, and being in S, A is also in K. Okay. Now just like here we chose two indices I and J which are distinct, let us again just take two indices K and L which are distinct between 1 and n, such that K is not equal to L. Now we already know that the matrix ELL, being a symmetric matrix, is in K, and just now we proved here that EKL is also in K, where K is not equal to L, and A is also in K because K is the subring, it's closed under multiplication. So this product also belongs to K. Now let us calculate this product. Let's see ultimately what matrix it turns out to be. So we start the calculation. EKL times A times ELL. Do not get afraid by looking at these expressions, okay? Let us recall that these matrices Eij form a basis of the vector space Fn. I mean, our algebra Fn is, after all, I mean, it's a ring, but it's also a vector space, being an algebra, and it has this basis consisting of n square elements. And the way we can express a matrix A as a linear combination of these basis elements is absolutely straightforward. It is just this, and in this you understand that this I and J are two independent indices, so it's a double summation actually. So they vary, both of them vary from 1 to n independent of each other, and accordingly you have many terms, n square terms in this linear combination. Then what we do, say we multiply this sum from the left side by EKL. What permits us to do that? Left distributive law in our algebra. And actually, first of all, EKL will be multiplied with alpha ij times Eij, and then you can take alpha outside. Recall that there is, I mean, this is possible because we are in an algebra. There is that last algebra axiom, you go back to the definition of algebra, that has to be used here to shift the alpha ij from this to that. In other words, EKL penetrates this defense of alpha ij, I can express it that way, and it gets multiplied with Eij. Now note that K and L are fixed, but I and J are varying, and just now we saw what happens when we consider this product. This product is 0 if the inner indices are different, but is not 0 if the inner indices are same. Now what is the inner index? The inner index is I. That means if I is not equal to this fixed L, then these products are 0. So many terms from this linear combination are now going to vanish, namely those corresponding to the i's which are different from L. However, for those i's that are equal to L, this will happen. Because if this I is L, then you are looking at EKL, ELJ, and you know that that product is EKJ. So that way we have this. And because I has been spent, so the only index J is left here. The others have vanished because they are 0. We still have a sum, however, and you can see that because we are only considering the I value L. So here also, instead of writing alpha ij, I have written alpha lj. The ELL is still sitting outside. Okay, it's waiting for its turn, and now it will do something. It multiplies this sum from the right side. Again, right distributive law and all the other algebra axioms have been used to finally have this sum. Here also something like that will happen. EKJ times ELL, note that here K and L are fixed, only J is changing. This product will be 0 if J is different from L, but will be non-zero only for that one J value which is equal to L. And accordingly, here also in this sum also, or I should say linear combination, almost everything vanishes except one term which corresponds to J equal to L. So I put J equal to L here, alpha Lj becomes alpha LL, and what will happen to this? Now this looks like means it is EKL ELL, and that will be equal to EKL, the outer indices. But what was this alpha LL? In fact, every alpha ij is equal to alpha. So this product turns out to be equal to this. But what did we see about this product before we started this calculation? That it's an element in our subring K. So that way you see that alpha times EKL is also in K, because that's what this is, right? Initially we did not quite understand how to prove that alpha times EKL is in K, where K and L are different. There it was Ij, but because here I decided to use I and J as variables in the summation, so I took some other things, KL. So we have now got what we wanted. And now how can we use all these things? So finally we take any matrix B in Fn. There is no restriction on B. B is just about any matrix, any element of Fn. And say it's ith row jth column entry B, beta ij. Then you can express B like this. And what did we find just now? That if the indices I and j are different, then no matter by what scalar we multiply the matrix Eij, the resulting product is in K. And in the beginning of the solution we showed that any scalar times Eii is also in K, and K is a subring, so K is closed under addition. So this sum is also in K. So any element in Fn is in K. So Fn is a subset of K, but K being a subring of Fn is itself a subset of Fn. So that way K is equal to Fn, and that completes the solution.